Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks. And the topic of the question is electromagnetic theory. The question is, a plane electromagnetic wave of wavelength lambda is incident on a circular loop of conducting wire. The loop radius is small a, where small a is very less than the wavelength lambda. The angle in degrees made by the Poynting vector with the normal to the plane of the loop to generate a maximum induced electrical signal is, so we have to find the angle made by the Poynting vector with the normal of the plane of the loop to generate a maximum induced EMF. Let us see how to solve this problem. Let us consider a small loop having radius small a lying in the xy plane. The normal to the plane of the loop is along z direction, and that is denoted by n cap. Now the magnetic field vector, that is B vector, of the incident EM wave on the loop is making an angle theta with the normal to the plane of loop. According to the Faraday's law of electromagnetic induction, the induced EMF is given by E equals to minus d phi b dt, where phi b is the magnetic flux, that is denoted by surface integral of the magnetic field vector, that is B vector. So induced EMF E is equals to minus d dt of surface integral of the magnetic field vector, that is B. We can write this induced EMF as E equals to minus of surface integral del B del T dot product with the elementary surface vector, that is ds vector. Now n cap vector is along the ds vector, so we can write it as minus of surface integral of del B del T dot product with n cap times ds. So if we just write this dot product in terms of the magnitude of these two vector and angle between them, then we can write it as E equals to minus of surface integral del B del T ds cos theta, where theta is the angle between this V vector and n cap vector. Now if we have seen the expression for the induced EMF generated by the EM wave on a loop, then we can see to generate the maximum induced electrical signal, that is EMF, the angle theta should be 0 degree. That means the magnetic field should be parallel to the n cap, or 180 degree, that is the magnetic field is anti-parallel to the n cap, so that the magnitude of the induced EMF will be maximized. Then in that case cos theta will be either 1 or minus 1. Now if the magnetic field vector B is along parallel or anti-parallel direction with the normal to the plane of the loop, the electric field vector of the EM wave will be in the xy plane, that is in the plane of the loop, since the electric field vector and magnetic field vector is mutually perpendicular for a TEM wave, that is transverse electromagnetic wave. So till now what we have seen, our magnetic field vector is along the or antiparallel to the normal to the plane of loop, and the electric field vector will be in the plane of the loop. Now Poynting vector for an EM wave is given by S vector equals to 1 by mu naught times E cross B. Now our if we consider the magnetic field vector is along n cap direction and our electric field vector in the xy plane, then E cross B will also be in the xy plane, and that will be same case if our magnetic field vector is antiparallel to the n cap direction. So S vector will be in the xy plane, that is in the plane of the loop. Hence, S vector will make 90° with the normal to the plane of the loop to generate a maximum induced EMF. So we have solved this problem and we found that the angle in degrees made by the Poynting vector in the normal to the plane of the loop to generate a maximum induced electrical signal, that is induced EMF, is 90°. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 1 mark and the topic of the question is electromagnetic theory. The question is, if E vector and B vector are the electric and magnetic fields respectively, then E dot B is option A, odd under parity and even under time reversal, option B, even under parity and odd under time reversal, option C, odd under parity and odd under time reversal, and the last option, option D, even under parity and even under time reversal. So let us see how to solve this problem. So E vector is the electric field vector, that is polar vector. So polar vector is related to the direction of motion of a system, that is translational motion, and that has a particular starting point. But magnetic field vector B vector is an axial vector or pseudo vector. So what is the axial vector? It is related to the direction of rotation of body. It doesn't have any starting point, only it has a direction along an axis. Now we will be talking about the parity operation and time reversal operation. First, starting with the parity operation. Parity operation or the transformation is the space inversion or reflection. It means flip in the sign of spatial coordinates. So if we consider p cap as a parity operator, so it will turn the position vector r vector into minus r vector. So it will flip the sign. Now we will be talking about time reversal operation. It means the operation of replacing the time with its negative value. That means t will become minus t. So that it indicates an phenomena in which time runs in backward direction or all the motions are reversed now. So if t cap is the time reversal operator, so it will give minus t upon acting on the time. Now consider a particle of charge q moving with a velocity v in an electric field E vector and magnetic field B vector experiences a Lorentzian force that is given by this expression. Force F vector equals to q times the electric field vector E plus v cross B. Now force can be written as mass of the particle times acceleration, and acceleration is d2r dt2. Now if we replace the r vector, that is position vector, by minus r vector, then the force will be m times d2 of minus r dt2, and that will give minus of m d2r dt2. So this will be basically minus of force vector. Now if we replace the time by minus t, then force vector will be m times d2r d of minus t square. So this will be m d2r dt2, and that is same as the force vector, that is F vector. So what we have learned, if we operate the parity operator on the force vector, so that means force vector will flip its sign under space inversion or deflection. So this will become minus of F. But under time reversal operation, the force vector doesn't change its sign. Now coming to the Lorentz force, that is F vector equals to Q times E plus V cross B. Now charge doesn't change its sign under parity operation as well as time reversal operation. So in this force there are two parts, one is electrical force, one is magnetic force. So we will denote it by 1 and 2. Under parity operation, F will change sign, that we know already. So from that information, in this part 1, the E will flip its sign because F is changing its sign under parity operation. So E will obviously change its sign. In 2, Q into V cross B will flip its sign under parity operation. Now V, that is velocity, is dr dt. Under parity operation, V will change its sign, that is minus V, because R is replaced by minus R here. Now under time reversal operation, the velocity will also change its sign, so it will become minus V. Now in 2, the term Q into V cross B, under parity operation, it will change its sign because force will change its sign, that means it will also change its sign this term. It means the magnetic field vector will remain unchanged because velocity is changing its sign. So that will give the negative sign here. So B has to be invariant under parity operation. So what we have learned till now, under parity operation, the electric field vector changes its sign. So it is odd under parity operation, but magnetic field vector doesn't change its sign under parity operation. So it is even under parity operation. Under time reversal operation, the force vector doesn't change its sign, but the velocity vector changes its sign. So it will turn into minus V under time reversal operation. So this suggests that the electric field vector E will not change its sign under time reversal operation, but the magnetic field vector will change its sign under time reversal. So magnetic field vector will change its sign because here V is also changing its sign under time reversal operation, and magnetic field also changes its sign under time reversal operation, and both this cross product will become positive under time reversal operation. That means force will not change its sign. So what we have learned, electric field vector doesn't change its sign under time reversal operation, so it is even under time reversal operation, but magnetic field vector changes its sign under time reversal operation, so it is known as odd under time reversal operation. So in a summary, what we have, under parity operation, E, that is electric field vector, flips its sign, so it will become minus E vector, but under time reversal operation, it doesn't change its sign. In the case of magnetic field vector doesn't change its sign under parity operation, but under time reversal operation, it changes its sign. Now coming to the main part, that is the dot product with electric field vector E and magnetic field vector P. Under parity operation, on this E dot B, that quantity, it will give minus E dot product with B, because parity operation will give minus E, but B will remain the same. Effectively, under parity operation, the quantity E dot B will become minus E dot B. So this is odd under parity operation. Now we will operate the time reversal operator on this quantity E dot B. The time reversal operation will give E as E vector, so E will not change here, but B vector will flip its sign, so it will become minus B vector. Effectively, we will get minus E dot B. So under time reversal operation, it is also odd under this operation. So effectively, what we are getting under parity operation, E dot B will become minus E dot B, that is odd under parity operation. And under time reversal operation, this quantity E dot B will become also minus E dot B. So it is odd under time reversal operation as well. So according to our solution, the E dot B is odd under parity and odd under time reversal. So our option C is the correct option for this question. This question was sent by one of my student Harish, and we'll be discussing this question. The question is, the spin orbit interaction term of an electron moving in a central field is written as f as a function of r times L dot s, where r is the radial distance of the electron from the origin. Here L is the orbital angular momentum vector and s is the spin angular momentum vector. If an electron moves inside a uniformly charged sphere, then option A, this Fr is constant. Option B, Fr is proportional to r to the power minus 1. Option C, Fr is proportional to r to the power minus 2. And the last option, option D, Fr is proportional to r to the power minus 3. So let us see how to solve this problem. This spin orbit interaction term of an electron moving in a central field written as F as a function of position times L dot S, where r is the radial distance of the electron from the origin. Now for a general potential Vr of a central field, the spin orbit coupling term is given by H Ls equals to 1 by 2 m square c square times 1 by r times del v del r times L dot S. So this is the Hamiltonian for a general potential Vr in term of spin orbit coupling. So here HLS is 1 by 2 m square c square times 1 by r times del v del r times L dot S. So our 1 by 2 m square c square times 1 by r del v del r, it is Fr denoted by Fr. So Fr is proportional to 1 by r times del v del r. We have to find this function f as a function of small r for an electron moves inside a uniformly charged sphere. So let us consider a uniformly charged sphere with total charge q. So the charge density will be rho equals to q by 4 by 3 pi capital R cube, where capital R is the radius of this sphere. Now we want to calculate the electric field and potential at a position r from the origin. So we can easily calculate this. We will not discuss much here. From using the Gauss law, we can calculate the electric field vector at a position r is given by 1 by 4 pi epsilon naught times q r by capital R cube along the r cap direction, that is radial direction. And also we can calculate the potential by knowing this electric field vector at a position r, and that will become v as a function of small r equals to q by 4 pi epsilon naught times 3 capital R square minus small r square divided by 2 capital R cube. And also this electric field is conservative electric field, so E can be related to the potential that is given by E equals to minus del V del R. Now we have seen the function f as a function of small r, that is proportional to 1 by r times del V del R. Now E equals to minus del V del R, so we can write f as a function of small r proportional to 1 by r times the electric field. Now in our case, for the electron moving in a uniformly charged sphere, the electric field is proportional to small r, that is position. So we can write f as a function of r proportional to 1 by r times r. So effectively this function f will become independent of the position, that will be constant. So option A is correct. So we have discussed the solution. So in our case, if the electron moves inside a uniformly charged sphere, then this function f will be constant in this spin orbit coupling term.